A system with a favorable expected lifetime does not guarantee individual system survival. Mean time to failure describes average behavior across a population of systems. It says nothing about the individual system path that crosses a catastrophic failure threshold. A single extreme load event can push a system into an irreversible failure state. Once that state is reached, the expected lifetime becomes irrelevant. Averages do not prevent absorption. System survival requires more than a favorable mean time to failure. Catastrophic fracture, corrosion through wall, and thermal runaway are absorbing failure states. Once reached, the system cannot recover. All future operational cycles become irrelevant after absorption. The tail of the load distribution governs exposure to these failure states. Rare but extreme loading events dominate long-run absorbing failure probability. The average load does not characterize catastrophic failure risk. Tail events define engineering irreversibility. A system with finite resource behaves like a finite random walk. Failure occurs when the resource reaches zero. Even under nominal operating conditions, catastrophic failure probability is strictly positive. Initial capacity determines how long the system can sustain adverse load sequences. A battery, a fuel tank, or a structural fatigue budget all impose a hard absorbing boundary. System survival is a question of path, not of expected resource consumption. Finite capacity defines the absorbing state. Under a light-tailed load model, extreme loading events decay exponentially. Under a heavy-tailed load model, extreme events remain significant for much longer. Earthquakes, storm surges, and electrical spikes are heavy-tail loading events. Standard deviation of the load distribution may be finite, while catastrophic failure risk is not well characterized. Tail shape of the load distribution governs absorbing failure exposure, not average load variance. A short operational test window cannot reveal long-run failure probability. Over a finite horizon, failure probability depends on initial capacity and the load distribution. Over an infinite horizon, the probability of encountering an extreme load approaches certainty. Positive drift in system health reduces failure probability. It does not eliminate it. Time increases exposure to absorbing failure states. It does not provide protection. Mean time to failure and variance-based reliability metrics measure average and dispersion of failure times. Catastrophic absorbing failure modes are structurally different from statistical dispersion. A high mean time to failure does not imply low catastrophic failure probability. Low variance does not imply safety from absorbing failure states. In heavy-tailed load processes, variance may be finite, while catastrophic failure probability is structurally determined by the tail. Moment-based reliability metrics are structurally blind to absorbing failure modes. They measure dispersion, not survival.